So hello everyone, welcome back to our data visualization series. If you have been following along, we have already covered various fundamentals and advanced plots in our previous videos. We explored bar plots, histogram, scatter plots, box plots, violin plots, heat maps, pair plots, donut charts, and additionally, we used plotly in the last video to visualize map plots. Now in this video, we will focus on more advanced time series visualization, including line plots, step plots, area charts, density plots, and the bubble charts. So these types of plots help us analyze trends over time and visualize multiple dimensions of our dataset simultaneously. And by the end of this video, you will be able to create and interpret these plots effectively, helping you analyze whether trends or any time series data with ease. So let's get started. Before we dive into the plots, we need to ensure we have required libraries. Since we have already covered this in previous videos, we won't go into much detail. So we are using pandas for data handling, matplotlib for visualization, and seaborn for its enhanced styling capabilities. So these libraries are essential for any data visualization project. Seaborn in particular provides more aesthetically pleasing and easy to read plots compared to the plain matplotlib. We begin by loading our dataset, which contains the weather history data. Since this dataset includes a formatted date column, we must ensure that it is in the correct date time format before we proceed with time series visualization. So here, to read the dataset, I am using here a pd.read_csv function. Then I am converting the formatted date column to date time format. It ensures that Python understands it as a time-based column. And then here I am sorting the dataset by date, which is essential for time series analysis. If date is not sorted chronologically, line plots may not provide meaningful insights. Now let's see how to create line plot. A line plot is one of the most effective ways to visualize how a numerical value changes over a continuous period. In our case, we are interested in analyzing temperature fluctuation across different time intervals. So a line plot allows us to identify patterns, seasonal variation, and long-term trends in the datasets. So this kind of visualization is especially useful in our weather analysis, stock market trends, and any scenario where tracking variation over time is essential. So by plotting temperature against time, we can observe if there are seasonal peaks, abrupt changes, or consistent patterns in temperature variation over the years. Now let's write the code for creating line plot to analyze temperature trends over time. Here I define the figure size. Now to create a line plot, we need three components: a dataset containing time series data, a clearly defined x-axis represents the time component, and a y-axis represents the numerical value we want to analyze. A line plot helps in identifying trends, seasonal patterns, and fluctuation over a period. So in this case, we will be plotting temperature changes over time using the sns.lineplot function from Seaborn. So this function allows us to draw a continuous line connecting data points, making it easier to observe trends. And the x-axis represents the formatted date, will hold the time-based data, and the y-axis will display the temperature value. Here we specify color equals to B to make the line blue, ensuring good contrast with the background, and line width equals to 2 to enhance visibility. Now to improve the readability, we use a plt.xtix rotation equals to 45, which rotates the x-axis label by 45 degree. Now let's execute the code. Here you can see the output, which is a smooth line plot depicting a temperature variation over time, and the plot visually represents how temperature changes across different time periods, helping us analyzing seasonal trends, sudden temperature spikes, and gradually increase or decrease. So this plot is particularly useful in identifying long-term weather patterns and possible anomalies, such as extreme cold or heat waves. And the x-axis represents formatted date which contain the chronological data, while the y-axis represents temperature, indicating the temperature recorded at each time interval. And the continuous blue line helps us observe these changes clearly, showing whether the temperatures has increased or decreased over the years. By using color equals to B, we ensure that the line is blue for better visibility and contrast against the white background. And the line width equals to 2 parameter make the line thicker, preventing it from appearing too thin or faint. One crucial aspect of the visualization is label rotation using plt.xtix rotation equals to 5, which rotate the x-axis label by 45 degree to prevent overlap and the improve readability, especially when working with the dense time series data. Without these adjustments, the date values could appear cluttered, making interpretation difficult. Looking at the generated plot, we can identify trends such as a periodic function, which may correspond to seasonal temperature changes and sudden spikes or dips, which could indicate extreme weather events. So, the resulting plot provides a clear and intuitive way to analyze temperature pattern over time, making it easier to draw meaningful insights from our dataset. So now let's move on to the next plot, which is step plot. A step plot is useful when we need to visualize discrete changes over time, rather than a smooth continuous trends. Unlike a regular line plot, which is directly connects data points with a continuous line, and a step plot display changes using a step pattern, making it easier to see abrupt shift in data values. So this is a particularly useful in a financial market analysis, stepwise progression, and in our case, atmospheric pressure changes over time. So here we start by defining the figure size using plt.figure function. Figure size equals to 12.6 to ensure our plot is large enough for readability. Next, we use the sns.lineplot function from Seaborn, which we have used previously in the line plot. However, this time here we used pressure columns. And then we add a new argument, draw style equals to steps dash mid. So this parameter changes the way the data points are connected, ensuring that each changes in pressure appears as a distinct step rather than a continuous transition. And the color R makes the line red, improving contrast and making it visually distinct from other plots. The line width equals to 2 argument ensure that the line is thick enough to be clearly visible. After plotting the data, we label our x-axis using plt.xlabel date, font size equals to 12, and ylabel function pressure font size equals to 12. So this make it clear what each axis represent. And the title, step plot of pressure over time, is added to provide a context to the visualization. As in the previous plot, we use plt.xsticks rotation equals to 45 to rotate the date labels on the x-axis by 45 degrees. Now let's execute the code. Here you can see the output, a step plot displaying how pressure changes over time. Unlike the smooth line plot for temperature, this plot shows a distinct, abrupt changes in pressure values. So this helps us observe clear shift in atmospheric pressure, which may correspond to weather events such as storms or sudden pressure drops due to the environmental condition. So looking at our plot, we notice a sudden drop in pressure at a specific point, which could indicate an extreme weather event or an error in a data collection. So this type of visualization is crucial for analyzing pressure variation, identifying anomalies, and understand atmospheric patterns in a meteorological studies. Now let's move on to our next chart, area chart. An area chart is a variation of line plot where the space beneath the line is filled with color, making it easier to see the magnitude of values over time. So this type of visualization is useful in identifying periods of high or low values and is commonly used in weather reports, stock market trends, and the financial analysis to depict trends more vividly. In our case, we are plotting wind speed over time to observe fluctuation and trends. So here we begin by setting the figure size using plt.figure function to ensure a clear and readable plot. Next we use plt.fill_between function, which is a core function in matplotlib to create an area chart. So this function fills the area between the x-axis, time, and the y-axis, wind speed. The first argument, d of in square bracket, column name formatted date, specify the x-axis, and while d of in square bracket, wind speed, represent the wind speed values on the y-axis, and the color equals to green, argument sets the fill color to green, making it visually distinct, and the alpha equals to 0.4 parameter centroid the transparency of the fill area, ensuring the underlying grid and the data points remain visible. Label wind speed. After setting up the plot, we label the x-axis and the y-axis using plt.xlabel function and plt.ylabel function. And the title, wind speed over time, is added to provide the context to visualization. Just as we did in previous chart, here we use plt.xticks rotation equals to 45 to rotate the date labels on the x-axis by 45 degree. And finally, plt.legend function is included to display a legend that help identify the chart elements. Now let's execute the code. Here you can see the output, an area chart that effectively display wind speed variation over time. Unlike a line plot, that only show a single curve, and the filled area in this chart emphasizes the magnitude of wind speed fluctuation, making it easy to spot peaks and the low points. So this type of visualization is particularly useful in meteorology for analyzing wind intensity patterns, identifying storm periods, and understanding weather fluctuation. By examining this chart, we can easily detect periods of high wind activity and observe how wind speed changes over time. Now let's move on to our next plot, KDE plot, which is also called density plot. So a density plot or a kernel density estimation plot is a smooth curve representation of a distribution. It works similarly to a histogram, but instead of showing the frequency of data in bars, it uses a continuous line to depict the probability density function of the variable. In our case, we are going to analyze the distribution of temperature values to understand which temperature ranges occur most frequently in our dataset. First, we define the figure size using the plt.figure function to create a clean and readable plot, just like in the previous visualization. Then we use sns.kde plot function from the seaborn to draw the KDE plot, and the input df in a square bracket, column name temperature, specify that we want to visualize the distribution of temperature values, and the parameter shade equals to true fills the area under the KDE curve to give it more emphasis. Use color equals to purple to make the plot visually distinct. Fill equals to true, ensure the area beneath the curve is colored, and the line width is set to line width equal to 2 to ensure the curve is smooth and clearly visible. Now we label the axis using plt.xlabel function and plt.ylabel function. And add a descriptive title using plt.title function. The x-axis represents the range of temperature values and the y-axis represents the density, which indicate the relatively likelihood of each temperature range occurring in the dataset. Now let's execute the code. Here you can see the output, a smooth bell-shaped purple curve representing the density of temperature values. Unlike the histogram, which might look blocky and depend heavily on bean size, the KDE plot provides a more fluid view of the data distribution. You can easily identify the most common temperature ranges. These are represented by the peaks in the curve. So this type of visualization is widely used in the data analysis to examine the shape of data distribution and is especially useful in comparing multiple distributions. So it is also commonly applied in finance, for example, to estimate the probability distribution of stock returns. And in our case, it gives us a clear idea of where the majority of temperature observation falls, helping us understand the overall behavior of the weather data. Now let's move on to our next chart, bubble chart. So this will be the final chart in our video, and it's a quick powerful visualization because it allows us to compare three numerical variables at once. Bubble charts are essential an extension of scatter plots where each data point is represented by a circle and its size encodes the value of third variable. In our case, we will be plotting temperature on the x-axis, humidity on the y-axis, and using the size of each bubble to represent wind speed. So as usual, we begin by setting the figure size using plt.figure function. Figure size equals to 10 and 6. So this ensures our plot is a sufficient size of visual clarity. Next, we use sns.scatterplot function to create a bubble chart. And the argument data equals to df, specify our data set. The x equals to column name temperature. And y equals to humidity, argument define the axis, just like we did in earlier charts. So what makes this chart unique is the addition of size equals to wind speed. So which set the size of each bubbles based on the wind speed values. This means larger bubble indicate higher wind speed. We also use hue equals to humidity, which color the bubble based on their humidity values. And the palette equals to cool warm, apply the color gradient that move from cooler to warmer tones. Making variations in humidity visual distinct, and the alpha equals to 0.6 control the transparency of the bubble, allowing overlapping points to remain visible, and the edge color equals to black, outlines each bubble to improve visibility, and size equals to 20, 500 sets the minimum and maximum size for the bubble, ensuring a consistent and readable scale. Just like in previous charts, we label the axis and add a descriptive title to give viewer context about the data being visualized. Here we include a legend that describes what the bubble size means, placing it in upper right corner. And finally, we call plt.show function to display the plot. Now let's execute the code. So here you can see the output of a color bubble chart where each circle represents a combination of temperature and humidity, and the bubble size reflects the wind speed. Larger bubble indicates stronger winds, and while the color variations show different humidity levels. From this plot, we can observe patterns such as a higher temperature, often corresponding to lower humidity, and how wind speed may vary across those conditions. So this type of chart is especially helpful when analyzing how multiple environment variables interact with each other. So providing a clear multidimensional view of the dataset. So that's it for today's video. We covered the range of powerful and insightful visualization that are particularly useful for analyzing time series data. We begin with the line plot to examine temperature trends over time, followed by the step plots to visualize discrete changes in atmospheric pressure. Then we explored the area chart to emphasize the magnitude of wind speed values over time. After that, we move on to the TDE plot to understand the distribution of temperature values in a smooth and the continuous manner. And finally, we wrap up with the bubble chart that allow us to analyze three variables simultaneously: temperature, humidity, and wind speed, offering a rich multidimensional view of the dataset. I hope this video was helpful for you. If you have any questions, please feel free to ask in the comments below. Thank you for watching and see you in the next video.